Assalamualaikum and a very good day to all panel and audience. It is an honor for me today, standing in front of you to deliver a presentation. I would like to present about the course of MEC 602, the final year project 2. Before that, let me introduce myself first. I am Nurhuria binti Abdul Alim. My student ID is 2018425484. I am the Bachelor of Mechanical Engineering student from University Technology Mara. My project title is a review on near-net shape forming of biometallic materials. I have been supervised by Professor Madya Nuraini binti Wahab. I hope this presentation will give you guys the overview of the review. For the introduction, the rising in trauma victims and musculoskeletal diseases is linked to an increase in life expectancy, which is also linked to an increase in bone tissue engineering. Bone tissue engineering has the potential to treat bone loss caused by degenerative, surgical, or traumatic events. There is a need to improve the healing of major bone fracture as well as treat existing non-union problematic fracture. A variety of medical therapy are being studied in combination with tissue engineering techniques for bone repair. Bone has a difficult hierarchical structure based on a length and width scale, which include the micro scale, macro scale, and sub-micro scale, nano scale, and also sub-nano scale. The mechanical properties of nature bone vary greatly depending on age and bone part. The longitudinal direction of compact bone is stronger and stiffer than the transverse direction. The trabecular bone has a porous structure, and the porosity and arrangement of the individual trabeculae influence its mechanical properties. The objective of this review is to provide comprehensive knowledge and highlight the contribution of structure, properties, and application of the biometallic materials. And the last one is to study the pre-review on biometallic materials and its previous laboratory study. The review for biometallic materials. Biometallic materials are complex structures that provide interior protection for biological tissue in joint replacement, dental implant, orthopedic fixation, and sense. Biometallic materials have been utilized in the manufacture of medical devices for the replacement of hard tissues. Metal has progressively outperformed other materials in orthopedic surgery since the invention of listery aseptic surgical method. Depend on particular implant device, they may be utilized as temporary implants such as bond plate, screw, and pins, or the permanent implants, completely joint replacement. There are a few characteristics of biometallic materials. The first one is low Young modulus. The bond is 5 to 10 times undeservedly higher than the Young modulus of biometallic materials. Consequently, the density of the bond drops and the strength weakens because of stress shielding. Next is durability. Materials implanted in human bodies should functional during the entire lifespan of the implant recipient from the first moment of implantation. Implants are also supposed to have high corrosion fatigue strength and high fatigue corrosion fatigue strength, with a minimum release of fretting where practical. Next is non-toxicity. The release of metal ions and debris is likely to cause cancer, deformity, allergy, necrosis, calcification, and inflammation. Next is biocompatibility. The created materials should be compatible with life system and not cause physical injury, which cover all the negative impact a material may have a biological system component such as bond, extracellular and intracellular tissue, and also plasma ionic composition. Next, we move to types of biometallic materials. First is stainless steel. Stainless steel is the most common biomaterials tools because of its combination of mechanical qualities, corrosion resistance, and cost effectiveness as compared to the other metals. Stainless steel is the most commonly used materials for treating transit fracture. A significant usage of stainless steel materials may be found in the manufacturing of temporary implants. Stainless steel has a double density of titanium and its alloy. For the cobalt-chrome alloy, in terms of ductility and wear resistance, cobalt alloy outperforms titanium and steels. For the composition, there are three primary constituents, which are cobalt, chromium, and molybdenum. Cobalt-based alloy has a high Young modulus and great wear and heat resistance. Next is titanium and its alloy. The most often utilized biomaterials implant are titanium and titanium-based alloy. This is owing to its exceptional biocompatibility as well as other characteristics like its lightweight, high strength, and a young modulus near to bond. Because of this advantage, it is the preferred implant above the others. They also have a variety of uses in dentistry and medicine. The last one is ceramic. Ceramic can cover implant in order to improve implant adhesive to the bone host. They are mechanically stiff due to their hard, brittle surface and low elasticity. Next, we move to the fabrication of nano shape forming. The first one is metal injection molding. Metal injection molding has evolved into a proficient near-net shape forming of metallic components with complex form and superb characteristics. Metal, metal injection molding is a competitive manufacture process that combines the efficiency of injection molding with the flexibility of metal particle sintering to produce vast quantities of small, complex, and high-performance metallic components. Process metal injection molding is to ensure metal flowability into a mold cavity and to maintain the shape of the injection molded component until the sintered process begins. This problem is often solved by distributing the powder metals into a binder to create a paste that flows at high temperature and solidifies at normal temperature. The next fabrication of near-net shape forming is 3D printing. There are three types of 3D printing technologies that are widely utilized in medical application, which is selectively laser sintering (SLS), thermal inkjet printing (TIJ), and fusion deposition modeling (FDM). The use is to create dental implant and costume prosthetic. But now, 3D printing is utilized to manufacture bone ears, skeletons, wound pipers, a jaw bone, and more. Next is hot isotopic pressing. HIP is a manufacture technique that decreases metal porosity while increase the density of various ceramic materials. Consolidate titanium and titanium alloy powder with spherical powder particles that make powder pressing problematic. HIP disadvantage is the existence of residual porosity in the sintered component, resulting the relative low mechanical characteristic. Powder preparation for metal injection molding. Metal injection molding principal raw materials are metal powders and thermoplastic binder. The powder parameters utilized in metal injection molding are critical in process control. The powder properties of metal injection molding are particle shape, particle size, average particle size, density, angle of repose, and more. The binder of metal injection molding, polystyrene and low-density polyethylene are common binders in metal injection molding. Binders are classified into two broader categories, which are wax or polymer, and those based on polymer or polymer compound. Polymer used to form retention during the subsequent phase, where wax decrease feedstock viscosity and provide the optimal flowability during the injection molding stage. The requirements of binder are able to integrate high quantity of fine metal powder, allow for the removal of the primary binder, provide adequate strength after debinding using the backbone binder, and the cost effectiveness. Next is mixing in metal injection molding. Metal powder and binder components are the fundamental raw materials for MIM, which are mixed to produce the feedstock. The feedstock is created by mixing it with a plasticized binder at high temperature in a mixing device. Powder and binder components were played using a Z-blade mixer to create injection molding feedstock. This Z-shaped blade mixer is ideal for mixing, kneading, and dispersing high viscosity materials. The next step is injection molding. The MIM sector may benefit from the plastic injection molding industry substantial knowledge and technologies background. Metal injection molding is a cycle process that requires heating the material to a molten state before molding it into a desired shape. In the hopper, the material to be injection molded is inserted. Heat energy is provided via barrel heater and shear heating. Shear heating occurs as a result of shear forces acting on the material as it is moved by the rotating screw. The molten material flows along the screw to the chute zone, which is positioned between the nozzle and screw tip. When injection molding parameters such as injection pressure, injection speed, holding or backing pressure, and screw decompression are tuned, the materials progressively fills the mold. For the debinding, there are three types of debinding, which is thermal debinding, solvent debinding, and catalytic debinding. Mostly we are using solvent debinding, which is immersing the MIM component in a solvent that dissolves the binder ingredient is what solvent debinding in place at low temperature. Lower invest and operation costs result in competitive total processing costs. The last process is sintering. Heating process that combines the ground component, which is composed of separate powder particles, to generate the required strength in the finished product. The operation is carried out at temperatures that are higher than the metal's melting point. Sintering temperature, heating rate, sintering time, sintering environment, and cooling rates are all controllable factors throughout the process. The conclusion of this review is the metal injection molding technique is the ideal method for producing medical implants. This is due to its ability to produce compact size, high form complexity, medium to high surface polish, and moderate to near dimensional tolerance. Metal powder and binder were combined at high temperature throughout the mixing procedure. The feedstock had been injection molded well and resulting a green tensile bar. Without breaking, dropping, and sagging, the solvent debinding process removed the soluble binder from the molded component. Characterization of parts which are sintered revealed that the physical and mechanical properties of sintered materials can be used for medical implants.